Hi, my name's Tibs. I'm going to try desperately not to wander across the stage away from the microphones. I work for a company called Ivan. We're the trusted open source data platform for everyone. In more interesting terms, referring back to Karen Jax's excellent talk on Postgres earlier, we're one of those people who provide Postgres as a managed data platform. So I really liked that talk. And today I'm going to talk about my very beginnings of learning about machine learning. There is no expertise here. I'm right at the start of this. So the talk's going to be in 4 parts. There's an introduction and vague background. I will not explain machine learning to you. I won't take long to do that. I'll talk about how I followed a tutorial written by one of my colleagues to find pictures of me from photographs taken at our last company get-together. And then I'll look at why on earth would we use Postgres for this, because for a lot of people it's not obvious why we would make that choice. So I'm naturally an AI skeptic. I'm old enough that I was around in the last AI boom in the 1980s, when vastly overinflated claims were made, and it all collapsed and AI became a dirty term in the following AI winter. A lot of useful things did come out of that, though. Things like expert systems, knowledge-based systems, and so on. It's just the name AI became polluted. We've kind of got over that a bit now. We're going through the same game again. Let's hope we don't have the slump. So I've been very skeptical about all of this. My colleagues, however, have been convincing me I'm wrong. Things like quick prototypes of boring code. Someone else wrote it for you. It might not be perfect, but it's got partway there. Rewriting a paragraph in a different tone of voice or a different way, which is quite hard to do manually, having something that gets partway to that is really useful. Finding my face, like we're talking about today. This is based on a demo that one of my colleagues wrote. We have managed Postgres, which we have as a service. One of our engineers earlier in the year installed the pgvector extension for us, because he just spent a day doing that for fun. And we all got enthused about pgvector. My colleague Francesco Tiziot wrote a nice tutorial to go up on our developer center, and I read it and thought, ooh, I could make a talk out of that. Yeah, here we are. And recently, 2 weeks ago, I was at a talk where someone was demonstrating using the sound of a dog barking to find pictures and videos of dogs. That's multimodal comparisons. That's really quite exciting. So maybe I'm wrong about ML being only hype. And we've had other examples here today, the medical stuff earlier, which is a wonderful idea, the gait analysis. So I'm not going to explain machine learning, because that's at least more than one talk, maybe a lecture series. But I do have to talk about vectors and embeddings, because they're not terms we use in quite that way. So an embedding means representing something on a computer. I don't know why we use that term. So a vector embedding is a vector, an array of numbers that represents something that we're storing in a computer. And because we're humans, we tend to use, in machine learning, people tend to use vectors, embeddings. They use the terms interchangeably, and I will be no better, so I apologize if I'm inconsistent in my usage. Now, I'm not going to get into vectors too much, because this is not a maths course, but broadly we can describe the characteristics of things with numbers. And we should all be used to the idea that we can describe colors with red, green, and blue. How red is it? How green is it? How blue is it? But we can also describe words that way. We can say, is it a noun? So we can assign a number to what part of speech it is. How much is it to do with a subject? Is it very much about being an aristocrat, or is it more about being an ordinary person? Is it a word that has warm feelings, happy feelings to it, or a word with sad associations? You can make up a vector of these sorts of things and use that for analyzing text. You can say, for a picture, how much are there scaly things in it versus furry things? And once we've got a vector, once we've got an array like that, we can treat it as an arrow. So here we've got a vector that goes from the origin, 0, 0, 0, and it goes to this value, 583. I've got the order wrong. So this is presumably representing a color. Once we've got vectors, we've got arrows, we can compare them. So we can compare their length, we can compare their direction, And mathematics exists and is very well established as saying, once we've got vectors, we can compare them, we can add them, we can subtract them, we can do maths with them in a vector space. That is the nearest I'm going to get to explaining that, but it means that there are technologies that are already available that we can hijack for our own purposes. Now, how do you calculate those vectors, those arrays of numbers? Well, historically, we would do it by hand. And this was done for text analysis for quite a long time. And people would sit there and sort of categorize all the words and say, well, a king is sort of kind of very monarchy, and a queen is very monarchy, but also very female, and a slave is very little monarchy, and so on. That doesn't scale very well. And what we now have is the ability to, with machine learning, to train a machine learning system to recognize, in quotes, that a thing belongs to particular categories. And those quotes around recognize are very important. We have to be careful not to anthropomorphize this. We're not talking about a person we can reason with and understand. We're talking about a system that's obeying rules, no matter how opaque, to get to an answer. And that means that sometimes the answer can be surprising as well as wonderful. Because when we train the system, we only train it about the things we tell it. So if we train a system to recognize the faces of white men with beards and glasses, it's not going to do so well at recognizing the faces of black women who don't have beards and glasses. We have to remember that at all times. And this is one of the perils of machine learning if we go overboard and just assume it's something clever that's just pure magic. So finally, pictures of me. This is a picture of me, courtesy of our company photographer. I rather quite like the smirk on this one. So our aim is to be able to run an SQL statement something like this. We want to select file names from a table called pictures, order them by the embedding being near to this magic string of numbers, and we want the first 10 of them. That's our aim. Or pictorially, we're going to be in two stages. Our first stage is we take a picture with some faces in it. We extract the faces by some means. We recognize the faces out of it. We turn them into these embeddings, and then we store them in the database. And that's not perfect. For instance, in the previous one, you noticed I had two faces. Yeah, it only found 2 out of 3 faces. Maybe there's something not right with my mechanism. Also, when analyzing a group photo, I found these 2 wonderful faces. Remember, training and wonderful results. So these arrays I've been showing you, with this face recognition, the arrays are 768 floating point numbers. In my notes to this, which are at the URL at the beginning, I'll repeat at the end, I found an explanation of why 768, which makes sense, but basically it's a magic number. So there's quite a lot of floating point numbers. Actually, in the machine learning world, this is a short embedding. Stage 2 then is once we've got those embeddings stored in the database, we take a reference face, my Slack photo, find the face in it, calculate its embeddings, that's the same process we did earlier, use the select statement, and we should get out a list of file names. And we go and look at those and see if there's really my face there. So that's what we're after doing. So going back to the tutorial I was following, we're using OpenCV Python, which is a lovely package that wraps the OpenCV package. We're using image embeddings, which is a package that understands how to calculate the embeddings given an image. We are using a pre-trained model from the OpenCV GitHub repository that has how to recognize faces built into it. And I'm using Click to do my command line, and scicopg2 binary as the standard lovely program for a package to talk to Postgres. So back in the database, we have to remember to enable pgvector. It's an extension, that's easy. That obviously only works if pgvector is installed. If you're using Ivan for Postgres, yay, we've installed it. Your life is easy. If you're using something else, you may have to install it yourself. The pgvector homepage explains how to do that. It also tells you when it's likely to be installed already. We create our database table. So here we've got a table called pictures. I'm not very good at naming. It's got a key called face, which is the string we're going to use to identify each face. File name is the name of the file we found the face in, because that's the result we want. And embedding is the vector of 768 values that we're actually storing. So let's look at that first process. Program 1, we're finding faces and storing their embeddings. So I've got a nice program called find faces store embeddings. I did say naming was not my strong point. It takes a list of image files, and it takes how to find Postgres. So let's look at the code. So it's a main image, a main program. It's imported CV2 as the OpenCV package. So the first thing we do is, and then I'm going to go through this code bit by bit. Sorry, I'm getting confused there. So no, I'm wrong. So we start with the har cascade equals load algorithm. We load the algorithm, and then we get the image embeddings. So loading the algorithm, we look up that XML file, we read it in, and check it actually succeeded. We got it just in case the file was wrong or anything. So we return the har cascade, the model that we can use to recognize faces. We read the image in. This is a bug I discovered last night. That says the comment says we're converted to grayscale. The conversion there is not. I'm not going to go into that anymore. I need to amend this in my examples I was playing with. It doesn't matter because I'm consistent with this mistake in all places. Let that be a lesson to something. Also, don't read your slides late at night. To find the faces, we use the har cascade model we pulled in. To detect them, we pass in the image. The magic numbers there, you notice the min size at the end as a commented out value. That's from the original tutorial. I found 250, 250, which is the size to expect your pixels to look for. I found that a better size for me. These are numbers you would play with to tune finding faces. Once I've got the faces, I get a list back of X, Y, WH, so location and size in the original image. So I do some munging to get the file name out. I don't know what's happened with the spacing there. And then for each face, I convert it to a pillow image because image beddings wants an image. And then I crop it. I calculate the key for the face as the name of the file and the location and size of the face. And I store all of that in Postgres. And unsurprisingly, that turns into some SQL. So I've got insert into pictures, as you'd expect. On conflicts, I learnt about for this talk. On conflict says, if face key already exists, then don't stop, do an update in this instance. And that then says, set the file name and the embedding values to the ones you just gave me, excluded as a kind of virtual table of the values you just gave me. I didn't know about that until I was learning about this, so that's a thing I learned as well. So we've now got our faces in the our embeddings in the database. We need a program to find the nearby faces, the faces that are like the face. So I called it find nearby faces, aforesaid naming problems. It takes a reference face, and it takes the number of matches I want. So the first bit's very much the same. And we calculate the reference embedding from that face. This is essentially the same code we had before. I'm not going to go through it, except that we're hoping there's only one face. And because it's me in the real code, it doesn't say we hope there's only one face. It actually checks that I didn't get naught or more than one faces, because the rest of the program wouldn't work very well, so I raised an exception in those cases. And then I have to turn that embedding I get back, which is an array, remember, into something that SQL will understand. It wants square brackets with a comma-separated list of numbers. So that's just a very crude way of doing that. I can then do the SQL statement I talked about earlier to ask for the faces that had matched those. And then I can print out the file names that I got back. This is all very standard stuff. So how good was it? Well, if I give it, in one example, 779 files. It found 5,006 faces. Took about 21 minutes to run the first program. Those who are watching carefully will have noticed I was creating a Postgres connection for every time around the loop for every file. Don't do that. But if I only created one connection, that wouldn't last long enough. I should do it properly. That's not, yeah. And it took 3 seconds to find the 10 nearest faces, which is perfectly acceptable for playing code. I was really happy with that. So as I say, for the Wednesday at our company get-together, our logo's a cuddly crab, so it's called Crab Week. We had 779 photos that the photographers gave us that were good photos, and 5,006 faces. Of course, I went through them by hand to look for all the pictures of me. I found 25 that I thought were me. Some were in a crowd, 3 were over my back. I'm not expecting to recognize those. 2 were with a really good false moustache, and I'm not expecting to recognize those either. It found the first 10 matches. 9 of them were me. That's about the number I'd have expected. The last one out of those 10 is someone who isn't me but has a beard and glasses. Yay. So this is the first one it found. It's a me standing there looking like me. This is me in a group. This is one of the last ones it found, demonstrating it can cope with other people. I apologize for the way I've obfuscated people's faces. I do not have graphic image techniques of tools, so you just get white blobs over faces. Thursday, we had fewer photos, 574, and fewer faces. I found 7 that had my face visible, although in 4 of them I had dark glasses on. These glasses go dark in the sunshine. And in the first 10 matches, it found the 3 that I'd expect that had me with ordinary glasses on. They weren't all in the first 3, but I think that's not bad at all. So the first one is this, me looking down slightly sideways in an audience. I was quite pleased it found that, because that's not very like the front-facing image of me in Slack. And luckily, the photo that's used in the tutorial here, it found me in that photo too. I'd have been unhappy if it hadn't, because that would have meant I'd done something wrong. So was this a success? Yes, it did what I wanted. I learnt a lot. Obviously not everything was bug. I got not awful results with only a few hours' work, and I know what I can do next to improve it. Specifically, I'd add a switch to allow setting the face detecting parameters so I can experiment quicker without editing the file. I'd make a different table for each set of parameters, so I didn't have to keep deleting the content of the file of the table when I changed the parameters. And I'd add a switch to generate the reference space to that program so I could save it in the database. And then the finding ones, I'd add a switch to say which face to use out of the database to look for, and I'd add a switch to say which table to search. And I'd probably refactor the code a bit because I'd have more time, possibly to make it worse. So in many ways, the most interesting thing is why Postgres? This is the lovely Slonic. Because we know Python, we expect Python to be useful for ML because it's been chosen as a good wrapper language for that. It's really quite dominant. But we know Postgres is a general purpose database. It's not a dedicated vector database. But it is our favorite Swiss Army knife or hammer. As my colleague said, maybe hammers aren't good for stirring soup, but they're amazingly good at all sorts of things. So let's go through the reasons. Well, first, it's significantly better than nothing. If you're doing, I know that's faint praise, if you're doing stuff with embeddings and things, you're going to hit a point where you've got too many embeddings. These are 768 numbers of time to store in a text file, or even in memory. So you're going to hit a point where a database is needed. So you might as well start using that early. And if you just want a database, we all think, no, I think that Postgres is a good place to start. And we probably already have it. Or if we don't, we know how to run it. It's easy to get started up locally. There are lots of managed services. Yay, Ivan. And it's a transactional database. And you can SQL all the things. So you can do things like find me the things like this order, that's my machine learning part, that are in stock. That's traditional SQL. Or find the pictures of me taken in Portugal, Crab Week. Between these dates, that's the metadata from the photographs. Or find things that match these qualities, that's the traditional SQL, and choose the one most like this other thing, which is doing the machine learning second. And Postgres has optimization techniques you can apply. You can run analyze on a query and so on. You can still do that with pgvector queries. And last, indexing speeds up the use of embeddings. pgvector has 2 forms of index. It added the second HNSW just recently in pgvector 050. You can have exact nearest neighbors, which is a bit slower, or you can have approximate nearest neighbors, which is a bit faster. And I'm not going to try and explain the difference. Go read the pgvector documentation for that, because I don't know enough about this. And we should recognize this pattern as Python programmers. Work in your familiar space, Python or Postgres, until it's not suitable. And then once you've worked out how to do stuff, move on to something else, but only when you need to. So when shouldn't we use Postgres? Because that's an equally important question. Broadly, when it can't cope and when it doesn't do what you need. So when the vectors get too big. Vectors in pgvector can have 16,000 dimensions. And to ordinary humans like me, that sounds like a big number. But to people in the machine learning space, I don't think that does. They think that's a reasonably small number to be going with. And currently in pgvector, you can only index up to about 2,000 dimensions. So that's another constraint, because indexing speeds up your access when you're making a query. And there's a 32 terabyte limit on table size. And again, I think that's a scary big number, but machine learning uses up space very fast. And lastly, on this bit, pgvector is ultimately based on Postgres, which is a general-purpose database. So it's not optimized to this. But remember to profile before you decide whether you're going to get better by moving elsewhere, because your problem might be something else. And of course, there's only a limited number of distance functions in pgvector at the moment, and dedicated databases may have more. This is likely to change over the future. And lastly, your queries might not actually be usefully SQL. For instance, if you're working in the text field, OpenSearch may be your friend. And OpenSearch has a similar story for working with vector embeddings and so on, because they're quite enthusiastic about that for obvious reasons. And this is true for other things like ClickHouse and so on as well. pgvector isn't actually the only solution for Postgres. There's a company called Neon who do vector embedding stuff, and they produce PG embedding, which is another open source solution. It only has HNSW, and they've done a lovely article comparing their own HNSW to PG vectors. I like the fact that in this space the competition is friendly. People are not being rude to each other. They're saying, well, we've got this and you've got that, and here's a comparison. And bear in mind, this is all very new. Back in the day, so Jonathan Katz talks about this, vectors are the new JSON. Back in the day when JSON was first added to PostgreSQL, it was slow and clunky. Then we got JSON-B and all sorts of things. We have got more and more functions, and JSON in PostgreSQL is now really lovely. This is going to happen with vectors over the next few years. And it's a similar story with large blob support, which is still getting better as we get better and better at handling large chunks of data. I should acknowledge that Postgres is a trademark of, hey, Postgres Community Association of Canada, as is the lovely Slonic the elephant. The pictures were acknowledged earlier. And as I said, definitely have to acknowledge Francesco Tiziot, my colleague, for the original tutorial, which inspired me, and he's given me some good advice over this as well. I work at Ivan. The QR code at the top right is the QR code for the GitHub repository, which has these slides and notes, which have more stuff in there as well, a bit more explanation. If you go to the link at the top left, you can access our free Postgres service if you just want to play. And if you want other services, you also can get a free trial there for an extra $100 over the standard $300 and some extra time by using that link. We're hiring as normal, and thank you very much. And I've actually managed to end slightly early, so I can take a question or two.
Congratulations. Thank you, Tibs. Are there any questions from the audience? Okay, we've got one question over here.
Hello, it was really interesting, thanks. I noticed in your example, you just provided the one reference photo. Could you potentially provide multiple reference photos and improve the quality, or does it not work like that?
So following the tutorial I was doing, no. I'd have to work out how to do that. So that if I'm following on the game here, I mean, obviously you could buy a different reference photo. It doesn't have to be that one photo. No, that's a very good point, and I think is something I hadn't actually thought through properly. But yes, that would be interesting. I don't know is the answer. I'd have to go read the documentation to find out. And that's a very good thing to look at next. I'm actually going to remember that. Thank you. I did say I'm very much a beginner at this.
Thank you. Do we have any more questions? We've got about a minute or two to squeeze one or more at one or two in. Yeah, the person over there.
Thanks, that was really cool. With the bit you mentioned where you can blend SQL and vector sort of queries together, was your experience such that when you use this plugin, you want to make a table that has some kind of foreign key to join through in like a normal relational way to the other part of the query, or do you put them all together into one table? Is there a normalization pattern that you were using to make that work, or you'd recommend?
Okay, so the first point, I'm also a relatively beginner at SQL, but to my understanding, we're not doing anything special here. So the array data type has been in PostgreSQL for a very long time. I think it might even be one of the original data types. This is a specialization of array, as I understand it. So what it's doing is wrapping more functionality around array. So it's not actually as weird and wonderful as one might expect. It's relying on the fact Postgres is pretty clever already, I think.
Great, thank you. That was easy.
Okay, thank you. And time for one very, very quick, just final last question. question. Have we got anyone?
Go on, pick Harry for cruelty.
What's toast?
Oh, I can't remember what it stands for. Go on.
The oversized attribute storage technique.
Yeah, it reflects the fact that things get big and sometimes you just have a big chunk of data and you want to store it, and how do you do that? And the people behind Postgres have been thinking hard about that for a long time, and I'm afraid the last time I read a paper about it was about 5 years ago, which, so talk to Karen if you want to know more stuff, because she will know more about it. It's actually one of the very important things to think about when you're doing database design.
Thank you. I'm glad I wasn't the only person with that question. So thank you very much, Tibs. And we have a big round of applause to say thank you.